Welcome to the next session, my dear friends. So in the previous session we were discussing about the ozone. Here one more point in ozone we need to discuss. It is what is the when oxygen, this ozone, reacts with water. So what are the compounds that will form and how it disinfects the water. So let us see that, and then we will move on to the next method. So when this ozone reacts with water, it forms a compound. It forms a compound that is 2HO2. 2HO2. This is a very powerful disinfectant. And this O3 and this HO2 further reacts with O3. This HO2 further reacts with O3, then it will form HO, 2O2 plus HO. 2O2 plus HO. So these HO2 and HO, this HO2 and HO are hydroxyl free radicals. Hydroxyl free radicals. So they are very effective disinfectants. Hydroxyl free radicals means OH minus is absent in both of them. So these hydroxyl free radicals released into water, so they oxidizes all the microorganisms. They oxidizes so all the microorganisms. So this is how the ozone will kill the microorganism and purify the water. And next is treatment with metal ions. So metal ions. When the metallic ions such as silver and copper used to carry out disinfection, so silver and copper metals in its colloidal form, acts like a disinfectant. That means in a colloidal form means what? In powdered form. In its colloidal form means what? Powdered form. So in its powdered form it acts like a disinfectant. Okay. Now here silver or copper. So we generally use silver, and with that method we call it as electrocatadine. Electrocatadine process. We call this process as electrocatadine process. In this electrocatadine process, there will be an electrode. So there will be an electrode. So on this electrode, so silver in its colloidal form is coated. So silver in its colloidal form is coated on the top of this electrode. So this is silver catadine process. We also call it as silver catadine process or electrocatadine process. So this is colloidal silver coating. Colloidal silver coating we will do on electrode, and we will send a DC current into this electrode. We will send a DC current into this electrode. So this will act like a disinfectant. It will kill the bacteria. It will kill the bacteria whichever comes in its vicinity. Okay. So this is nothing but electrocatadine process. See, silver is very costly. So this process is also very costly, and this cannot also take care of any future contamination. Once the metallic ion interaction is over, that means when the water is leaving this chamber, as how the UV rays were in the same manner. So when it is in contact with this electrode, then the water is it is not contaminated. But once the water leaves this chamber, then there is no effect of this silver catadine on anymore. Okay, so that means the water is prone for future contamination. So there won't be no residual power here, no residual power. So the water is prone for future contamination. Is prone for future contamination. Future contamination. Okay. Now, so this is treatment with metallic ions. Next is treatment with potassium permanganate. Treatment with potassium permanganate or KMnO4. So potassium permanganate, treatment with potassium permanganate, that is KMnO4. It is KMnO4. So treatment with potassium permanganate, KMnO4. Here what we do is KMnO4, if you look at well waters, okay, generally if you see well waters during epidemics, they will distribute, the government will distribute a small packets of KMnO4. These days I don't know, but earlier days during the cholera epidemics and all, so they used to give us a pouch of this KMnO4, and we will add this KMnO4 to the especially well water, because during those days well water is a prime source of water for drinking. These days municipal water is coming, but earlier KMnO4 is the well water is a source of drinking water. So in that they used to periodically maintain the water, periodically disinfect the water by using this KMnO4, by adding this KMnO4 into a bucket of water. Okay, into a bucket of water we will first add the KMnO4 packet in that bucket of water, and then we will drop that bucket into the well and we will stir it using the bucket. okay, with a rope. So now what happens? So this KMnO4 will get dissolved completely into the well water. Now, so we need to increase the dosage such that the well water should turn into pink color. The well water should turn into pink color. Once the well water turns into pink color, that means the dosage of KMnO4 is now sufficient. That means when white pink color is coming, because the KMnO4 residue is present. So KMnO4 residue, if it is present, then it looks like a pink color. It looks like pink color. That means first you have added KMnO4, which is started utilizing by the water. So now if you are keep on increasing the addition of KMnO4, water will take the KMnO4 which you are adding. But at some point water's demand will completely satisfied, and still if you are adding, then the KMnO4 will present in the water in the form of a residue. That KMnO4 residue will look like pinkish color. So that is when pink color is appearing in the water, that means you have added sufficient amount of KMnO4. Until the pink color appearance, you need to keep on increasing the dose and add it. Okay. Once the pink color appears, then stop adding KMnO4 and leave that water untouched and unutilized for about 1 day of time. Generally, the KMnO4 needs 4 to 6 hours to kill the microorganisms, but anyways, we generally leave that water undisturbed for 24 hours. After 24 hours, we can consume the water. Likewise, we do the treatment of water using KMnO4. But here the problem is KMnO4 is effective in killing the cholera causing bacteria, but it is not that effective in killing the other kind of microorganisms. And another problem here is we are having manganese here, because of which it is turning into pinkish color. So if the dosage is more than residual metallic ion like manganese, if it is present, then it creates problem to the water again. That is why is the reason generally we don't use this for the municipal water supply. Two reasons. One is it cannot kill all the microorganisms effectively as it can kill the cholera causing bacteria, and one more thing is again it causes color to the water. That is the two problems why we don't use potassium permanganate for bulk water supplies. Okay. So it is a popular disinfectant for well waters. It is popular disinfectant for well water supplies. So KMnO4 is added to well water with an increasing dosage until the well water turns pink. The well water turns pink. So once pink color is formed, it indicates the residue of KMnO4. The residue of KMnO4, and the water is not used for KMnO4. The water is not used for next 48 hours, and the contact time of KMnO4 is 4 to 6 hours. So though the contact time is over, we don't take that water for 48 hours because there is residual KMnO4 which will take care of rest of the contamination which is coming into the water. Okay, that is why we don't disturb it for 48 hours. Generally the dosage is ranging from 1 to 2 mg per liter. The normal dosage of KMnO4 ranges from 1 to 2 mg per liter. So normal dosage of KMnO4 ranges from 1 to 2 mg per liter. It removes %, cholera causing bacteria, but kills 98% of other kind of bacteria, and microorganisms. Okay, so that is why generally we don't prefer this method for bulk water supplies. So next is treatment with halogen group compounds. So what are the halogens in a periodic table? In periodic table, just before the noble gases. So just before the noble gases there is a column. That column is nothing but halogens. So just before the noble gases there is a column in periodic table. So in that column there will be chlorine, bromine, iodine, bromine. So generally F2 fluorine 9, next then chlorine 17, okay, next bromine, iodine. So these are all the halogen group compounds. So all are good disinfectants only. All the halogen group compounds are better disinfectants only. But here all the halogen group compounds are better disinfectants because of greater affinity. Greater affinity to attain noble gas configuration. So here all these things I told you just one step away to become noble gases. So that is why they are having more affinity to electrons. And here that is why I have told you. So instability leads better disinfection capability and also greater affinity. So if you look at the halogen groups, they are stable molecular form. They are in their molecular form only, they are stable, but they are having very greater affinity to lose the electrons and becomes noble gases. To lose the electrons and becomes the noble gases. That is why they easily react with any kind of compound which comes in its vicinity. So generally the problem with fluorine is it may be better disinfectant, but it is harmful to human beings. It may be better disinfectant, but more doses of fluorine may cause fluorosis. So that is a problem associated with fluorine. It may cause fluorosis when it is more, because it is among all the compounds, it is much more effective. Because if you compare in the term of the periodic table, so that column is completely having the affinity. In that column again fluorine is much more effective. That is why it will react with calcium present in our bones and in our teeth, and they causes deformation of the bones, which is called bone fluorosis, or can cause deformation of teeth, which is called dental fluorosis. That is why generally we don't prefer this as a disinfectant. We will discuss afterwards about Cl2. Iodine and bromine. This iodine and bromine also used as disinfectant in the form of iodine and bromine pills. Iodine and bromine is used, are very powerful disinfectants, They are used in the form of iodine and bromine pills. So these bromine and iodine pills are carried by army troops. So they are carried by army troops, because army troops don't find a purified drinking water anywhere they go. So they will carry these iodine and bromine pills. They will take some kind of surface water or some kind of groundwater, anything. So in that they will simply drop these pills. So these pills will dissolve into the water and it will completely disinfect the water. So which can be easily consumable. So because these army troops will not get purified water at any location, so that is why generally they carry these iodine and bromine pills. But this is very costly method. Hence we don't prefer it for bulk water supply. Hence it is not preferred for bulk water supply. Okay. This is iodine and bromine pills. And the last method, that is, all are minor methods. The last method, that is major method, that is chlorination. Major method. Next is the major method. It is chlorination. Chlorination. Okay, so next method is chlorination. So here chlorination means addition of chlorine to the water. Okay, addition of chlorine. Chlorination means addition of chlorine Cl2 to water. So when we add Cl2 to water, okay, Cl2 reacts with water. Cl2 reacts with water only when the pH is only when the pH is greater than 5. Okay, only when pH is greater than 5. So when pH is greater than 5, then Cl2 added to water, it forms hypochlorous acid. So Cl2 plus H2O. So when the pH is greater than 5, then it forms HOCl plus OCl minus. So this HOCl is called hypochlorous acid. Hypochlorous acid, and this is hypochlorite ion. This is hypochlorite ion. This is a reversible reaction. When pH is not maintained 5, more than 5, then it will come back like this. When pH is less than 5, then it will become molecular chlorine. This is molecular chlorine. So this is called molecular chlorine. So when pH is less than 5, the chlorine Cl2 will exist in the form of molecular chlorine. That means it does not react. When pH is less than 5. So when pH is greater than 5, it has reacted. It has formed hypochlorous acid. This hypochlorous acid plus HCl, not this HCl, hydrochloric acid. So this is called hydrolysis. This term is called hydrolysis. So adding Cl2 to water is nothing but hydrolysis. This is hydrolysis. And once the hydrolysis is over, HOCl is formed. This HOCl again disintegrates into OCl minus and H plus. HOCl depending upon the pH. So this HOCl when pH is greater than 5, when pH is greater than 8, when pH is greater than 8, then it will disintegrate into the form of H plus ion plus OCl minus ion. This is called ionization. This equation is called ionization, and this is a hypochlorate ion. This is called hypochlorate ion. Again, it is also a reversible reaction. So it will go back when pH is less than 7. So again HOCl will form. OCl minus will not exist. So Cl2 exists in the form of, so when you add Cl2 to water, it is directly forming HOCl. Further, this HOCl is forming OCl minus. Okay, OCl minus. So Cl2 in the form of HOCl and OCl minus is called freely available chlorine. So Cl2 in the form of HOCl and OCl minus is called freely available chlorine. So these two are the disinfectants. HOCl and OCl are disinfectants and OCl minus are disinfectants, helps in killing of microorganisms. Okay, so if you compare HOCl and OCl minus, between HOCl and OCl minus, HOCl is powerful disinfectant. It is about 80 to 100 times more powerful. So HOCl, it is means what? HOCl is about 80 to 100 times more powerful than OCl minus. So HOCl is 80 to 100 times more powerful disinfectant than OCl minus. See here, generally why OCl minus is less effective than HOCl? Why OCl minus is less effective than HOCl? Because generally the microorganisms are very fine material. So microorganism is also a material which is very small and fine. So that is why microorganisms also carry some charge. So though the microorganisms are creatures, but they will also carry a charge because they are very fine material. So some microorganisms may be negatively charged. Some microorganisms which are, because negative charge is predominantly present in finer material. Negative charge will be predominantly present in a finer material. So that is why on microorganism also majority of the microorganisms carry negative charges. So when a negatively charged microorganism comes in contact with OCl minus, then OCl minus will not react with it because both are like charged. So that is why generally OCl minus is having greater affinity towards the positively charged particles. Maybe that positively charged particle may be an impurity or may not be an impurity, but this will go and react with that. So unnecessarily, that is why, so OCl minus target is to kill the microorganism, but OCl minus cannot effectively kill negatively charged microorganism, as well as it reacts with positively charged compounds which may not be impurities, which are not impurities. So that means OCl minus is unnecessarily wasting its energy in reacting with positively charged compounds which may not be impurities, and it cannot tackle the negatively charged organisms because this is also carrying a negatively charge. So that is why OCl minus is less effective than HOCl. HOCl is neutralized compound, it has nothing to do, only its work it will do, but here on the head of the OCl there is a negatively charge. So because of which this OCl minus agenda first priority is to get neutralized. So for getting neutralizing, it needs a positively charged compound. Whether it may be an impurity or not impurity, it does not matter. So only positive charge matters to OCl minus. That is why what happens, it may not be effectively work in the water as HOCl can do. So that is the reason why OCl minus is less effective. OCl minus is less effective, and the presence of HOCl and presence of OCl minus, how much proportion of HOCl is present, how much proportion of OCl minus is present will be decided by the pH of the water. So depending upon the pH of the water, the availability of HOCl and OCl minus varies. So let us see what is the ranges of the pH, and let us see the ranges of pH. Before moving on to that, before moving on to that, there are some reactions which are needed. Let us see now. See, generally HOCl being it is an acid, hypochlorous acid. It is an hypochlorous acid. So its proportion will be more. Its proportion will be more when the water is acidic and the water is acidic. So when the water is acidic, then that means pH is lesser, then HOCl will be more, and pH is lesser. So whereas OCl minus, when pH is more, its proportion will be more and the water is alkaline or basic or pH is more. So let us understand now what is the proportion of HOCl and what is the proportion of OCl minus in a water. So to determine that, first we need to write the equation of the reaction. So HOCl when reacts with water, it dissolves into the water and it forms H plus OCl minus. So for this reaction there will be rate constant. So rate constant for this reaction, rate constant K is equal to, see, always rate constant is nothing but concentration of products by concentration of reactants. So the concentration of products H plus ion and OCl minus by concentration of the reactant, that is HOCl concentration. If the same reaction is written in the other way, from the back to the forward, if you are looking it like this, then the rate constant will vary. Here for this equation, the rate constant is, product is HOCl and the reactants are H plus ion and OCl minus ion, and the reactants are H plus ion and OCl minus ion. So rate constant is nothing but the concentration of the products upon the concentration of the reactants. Now here from this, so I will take this reaction for our calculation. So K is equal to H plus into OCl minus by HOCl. Okay, so that means I can write this equation as K by H plus ion concentration is equal to OCl minus concentration by HOCl concentration. By looking at this equation also we can derive that, see, this is a constant, K is constant, so that means from this equation we can write that OCl minus is inversely proportional to H plus ion concentration. OCl minus is inversely proportional to H plus ion concentration, and HOCl concentration is directly proportional to H plus ion concentration. That is why, so OCl minus will be more when H plus is less and pH is more. Similarly here HOCl will be more when H plus is more and pH is lesser. So that is why we need the lower pH ranges. We need low pH ranges only in order to effectively work the chlorination. So in order to have effective chlorination, we need HOCl to be present more. That is why we need to keep the pH as low as possible, such that the chlorine efficiency will be more. Okay, so from here I can write the percentage HOCl. So this is the ratio of OCl minus and HOCl. If I want to find the percentage HOCl, see, percentage HOCl means, see, in this HOCl some amount of HOCl is becoming OCl minus. In this HOCl, depending upon the pH, some amount of HOCl is becoming OCl minus. Or completely HOCl is converting into OCl minus depending on the pH of the water. So if this HOCl, some amount of HOCl is converting into OCl minus. So now the leftover HOCl, if you take the leftover HOCl is leftover HOCl, I taking it as HOCl leftover. Okay, HOCl leftover by HOCl leftover plus OCl minus formed. So after this reaction, some part of the HOCl has become OCl minus, some part of HOCl has become OCl minus, and some part of HOCl remains like HOCl. Okay, that means HOCl, initially it is HOCl only, but it has disintegrated into OCl minus and it has disintegrated into HOCl. Some portion will remain as HOCl, some portion will convert into OCl minus. So I am taking this HOCl percentage, this HOCl. So this HOCl percentage is nothing but HOCl by HOCl plus OCl minus. Are you getting my point? Percentage of HOCl means initially the HOCl is formed from chlorine, but this HOCl is not sustaining like HOCl. Some part of HOCl is converted into OCl minus, some part of HOCl is still remaining like HOCl. So the ratio of percentage of HOCl, how much HOCl is present, that is nothing but percentage of HOCl, weight, concentration of HOCl by concentration of HOCl left plus concentration of OCl minus, that is nothing but the percentage of HOCl present in the water. Okay, now this can be written like this: 1 by HOCl, I am bringing it to denominator, so 1 by HOCl by HOCl, that is 1, plus OCl minus by HOCl. OCl minus by HOCl. Isn't it? If I bring this HOCl into the denominator, so this HOCl and this HOCl will get cancelled, and this OCl minus by HOCl will left over. So this OCl minus by HOCl is nothing but what? Nothing but K by H plus ion. So it is equal to 1 by 1 plus K by H plus ion concentration. 1 by 1 plus K by H plus ion concentration. This is nothing but percentage of HOCl. So the percentage of HOCl, percentage of HOCl is equal to 1 by 1 plus K by H plus ion concentration into 100. So if you know the pH of the water, we can say how much is the percentage of HOCl is present in that water. We can easily say how much percentage of water is present in the, how much percentage HOCl present in that water. So this is percentage. If I want concentration of HOCl, concentration of HOCl for a particular dosage of chlorine, for a particular dosage of chlorine. So Cl2 dosage, what is the Cl2 dosage you are taking multiplied with the percentage of HOCl, multiplied with percentage of HOCl. This is the concentration of HOCl. So what is the total amount of HOCl that will generated? What is the total amount of HOCl that is generated is equal to what is the dosage of chlorine you have added into, in that dosage how much is converted, how much of the chlorine is converted into HOCl. That is nothing but the concentration of HOCl. That is nothing but the concentration of HOCl. Again, this HOCl classification, so as it is dependent on the pH, so for a particular pH, what is the percentage of HOCl, what is the percentage of OCl, that is also, it is there. So we will discuss that in the next class, and we will also study more about this chlorination in the next class. Thank you so much.